Hello and welcome everybody to a new video. So this video we're going to start talking about my latest project, which clue from the title and what's on the screen in front of you here, it is an electronics project and I have designed this PCB. So right now this is just going to be a bit of an overview of like the design of this PCB and how I did it, a little bit about general design PCB stuff. This is the second PCB I've designed. First one, if you've watched my channel for a while, you might remember my series of videos on building a ball and beam kind of educational kit. I designed my first ever PCB for that. So this is effectively my second PCB design. And what this actually is a little bit of an enhancement and kind of a modularization of part of that original PCB. So yeah, this is it. We're going to talk about the design of it. Going to talk a little bit about getting it ready for manufacture and stuff like that, and yeah, that's pretty much it for this. I have just literally yesterday sent this off for manufacture, so it's gone off to JLCPCB, who are the provider that I've used before. So it's basically being manufactured in China, and then it'll be sent here to me in Ireland. So I think it should take about 2 weeks or so between manufacturing and delivery. So 2 weeks from now, I should get these, and then I'll actually know if they work or not. So as of right now, I don't know if this actually works. I think it should work because it's a copy of a design I did before, unless I've done something wrong in it. But yeah, pretty confident this should work, but I don't actually know as of yet. So 2 weeks time, I'll do another video where I get this and I have to put a couple of components on it, and then I can test it. We'll see if it works then. So everything I say about the design of the circuit in this video could be proven wrong in a couple of weeks, or I may have made some mistakes, but anyway, we'll find out. So with that said, let's have a look at the board and what we actually made. So this is our board. I'm in Fusion 360 here, or actually I think it's now just called Fusion from what I've seen. But Fusion 360 is what everyone knows it as, so I'm going to keep calling it that. And yeah, so I use the electronics toolkit in Fusion, which is basically Eagle, that's Autodesk's older EDA software. It's called Eagle. That's basically built into Fusion 360 these days, and that's what I use. But it does have this nice little plugin where it can, if you supply all of the right models and stuff in your setup, it can generate this little 3D rendering of your PCB, which is kind of cool. So this will give you an idea of what it is, and the clue from the name, it is a power supply module. So on my old project, the last project, the ball and beam one, I wanted a way of just having a simple like flick switch that you can turn on and off to power the whole thing. But part of that project was it was driving a stepper motor, and stepper motors and motors in general can draw quite a bit of current. So a very dumb approach to just switching something like that is your little small slide switch could just directly interrupt the power that's flowing through it, going to the motor. The thing is, that's not a great idea when you're drawing a fair amount of current, and these little switches aren't really rated for very high amounts of current. So you'll notice that if you have a switch that switches a lot of current, it's usually a fairly hefty kind of chunk type switch. It's not going to be one of these tiny little micro slide switches, which if you try to switch it a lot of current, you can burn out the internals of it, and then it's basically useless. So because of that, I designed a very special circuit, which is what these little transistors and resistors and capacitors in here are doing. It's basically a switching circuit that allows for the switch to only carry a very small amount of current, and then when you switch it on, it pipes a very tiny amount of current through these gates of these transistors and stuff, and allows the transistors to then conduct through a large amount of current without any big current flowing through the switch. So this is maybe a little bit abstract. It might be a bit clearer if I show you on the circuit diagram. I'm not going to explain it in huge detail how it works because it's a little bit complicated, but you should trust that it does work, basically. So I can connect the power directly to this, so the input power can be connected directly to these transistors, and then by flicking this switch, I can have a tiny amount of current flowing through the switch, and then effectively the transistors turn into a switch themselves, and they can allow themselves to conduct to supply the power for the rest of things. So the other things that this does, Very simple. It's got two voltage regulators, which you see here and here. One of them is a 5-volt regulator. The other one is a 3.3-volt regulator. So you can supply some V-in voltage, which can be between about 7 and 15, 12 really volts. And then you can switch on and off. The on and off switch will then switch whether you can get 5 or 3.3 volts out of it. Or sorry, when you turn the switch on, the V-in will be piped through the switching circuit to these regulators, and then you can get 5 and 3.3 volts out of it. So you can switch on and off devices that are powered by either 5 or 3.3 volts. And yeah, that's about it really. In this particular design, this switching circuit it's kind of a little bit overkill, because the devices that you'd be driving off this for 5 and 3.3 volts aren't going to be really high current devices. As a V2 of this, I'm probably going to add a 5th pin to the pin out. So there'll be a ground, V-in, there'll be 5 volts and 3.3 volts, but then there'll also be another pin, which will be like a pass-through of the input voltage, but out the back of the switching circuit. So at the moment, this V-in pin, no matter which one you connect it to, will always connect you directly to your source voltage. And no matter what state the switch is in, it won't switch that voltage. So as a V2 board, I'll probably make it 5 pins, and I'll have a switched version of that, which could be a switched, maybe like 12 volt supply. And then with that, you'd be able to power a motor off of it and then switch it on and off, and you'd be able to interrupt that like 12 volts and however many amps is going to be pulling. And this switching circuit should be good for that. Should be rated up to about 1.5 amps. So that's pretty considerable. If you're driving like stepper motors, small stepper motors and stuff like that, it should be enough. So this isn't a high power thing, but it should be good for microcontrollers, sensors, that kind of thing. Few LEDs maybe. Mostly kind of small desktop-y type stuff, which is a lot of what I use it for. That also should bring me to kind of the form factor of this. We see we've got a rail here and a rail here, and then another one here. So I know the way these pins are is this is the way they default come out in Fusion, but you can imagine that these would actually be soldered on the bottom, and then those two rails would fit across the middle bridge of a breadboard. So you can plug this into a breadboard and have a little power switch, which is handy. And then this top rail, I probably won't use it very much, but this header will allow you to basically jump power somewhere else to maybe another device. I plan to use this pretty much for that sort of thing. So I'll use it in a breadboard if I'm prototyping stuff, just so I can switch things on and off. And I'll probably also use it modularly on like a carrier board that it plugs into, and then I can use it to jump power to other things as well. Which will become then, when I do the V2, that'll have the switched like 12 volts or whatever the input on it, that will become very useful as well. So that kind of describes what it is, its form factor, and a little bit about how it works. So let's dig into the electrical design a little bit, and I can talk about some of like the manufacturing and stuff like that too. So if you start a new electronics project in Fusion, you get this. This is sort of the overview of the whole thing. So there's kind of 3 main parts to this. You've got our actual circuit diagram up here. So this is how I laid it out and all the parts and how they're connected. You've then got the PCB layout tool up here, which shows you where all the copper goes, how the components actually lay out on a physical board. And then this thing down here, which is just the auto-generated 3D model of that board that you've laid out. But before we do any of that, we have to do another thing, which is we basically need to configure what all these parts are going to be. So like when you start to draw something like this, so our schematic, it can be a little bit complicated because you need to figure out what the parts are that you want. So you can go to here and you can see like place components. So if I remove this filter here, if I go all libraries, you'll see that there's tons and tons and tons of components here that I can scroll between and find. And I can search for like OR, which is basically going to be like a resistor probably. I can scroll down, and it's actually just returning all sorts of different things here. So it's not even giving me exactly what I thought it was going to give me. But the thing is that all of these parts, we've no real idea about exactly what they are, what their electrical properties are, what their part numbers are. We don't know. We don't know anything about these really. They're just random collections of like libraries that come by default, and also some libraries that I've installed because I was trying to mess with stuff. It's all a bit complicated. So based on that, and also once you start to look at the manufacturing side of this, it becomes kind of difficult to get your head around. But what you can do, and this is what I found is the easiest thing to do, is to basically create your own parts library. So within Fusion, they give you this option where you can create a parts library. So that's what I've done for this project. And I've reused some of these parts from my previous project as well. But basically, a part, a component that you set up in this comprises of more or less three kind of things. The first thing is like this drawing. So this is this up here has an odd name, but this is basically a resistor. So a resistor, this is a symbol for a resistor. You can have also sometimes got a squiggly line. This is just a different type of symbol. It has 2 pins defined on it. Resistors generally don't have an orientation they have to be in. So they're just very simple like this. And that's the symbol that you'll see on the diagram. So when I drop this in, so if I dragged and dropped it from over here and popped it in here, it'll end up looking like this in my diagram, a resistor. This is labeled R1, and I said it has a value of 20k, but that's just simple resistor component. So in my library, I've had to configure this. The other thing that you have to then configure to make this work is you need to configure its footprint, which is this thing over here. So a resistor could be loads of different shapes and sizes and all sorts of different things. Like this is a surface mount resistor component, which is what I wanted because I'm having these assembled automatically, and you can only get surface mount components assembled automatically by the provider I'm using anyway. So I have to use this. But a resistor could also be like, the classic resistor shape you would have seen, which is, a little barrel shaped thing with 2 wires coming off the ends of it. So if I just drag this into my schematic, I don't know if it's linked to the type of resistor that I need it to be linked to. So that's why when you set up in this parts library, you have to also set up that it is linked to this type of footprint. So these you can draw these, and that's what part of the software lets you do. So you can expand this out, you see, and I can have a look at so that's the schematic, and then you can click in, and this is the footprint. So you see here, you can do like add the copper pads, add these little silt screen traces, and then you can add names and values and stuff, which will all be printed on the board when you drag and drop it in. And then the final thing is, I'm not going to do that, is you've got these little 3D models. This is very specific to Fusion, the way it works in this instance, because these are what get rendered in my view here. So that little resistor model gets rendered here on the board. But that wouldn't be the same. That's not the same everywhere. And a lot of software won't give you this nice like 3D rendering, it's kind of pointless. It doesn't really do anything for me, but it does let me kind of, move it around and make sure things look right in the right places and stuff like that. And it's kind of cool as well. But anyway, the other key point about this, so we have our symbol set up. We know what it is electrically. We know this is a resistor. We have a symbol. We have its pins. We have the pads set up so that we know how it's going to be when it's on the board. The final key thing that we need to know about is what the part actually is. So this is a little bit into the manufacturing side now of things. But when you want to get a PCB manufactured, you can't just tell the manufacturer, I'll put a resistor there. They need to know, well, what resistor do you want there? And that's for a lot of reasons. They obviously need to know, what value it is, whether it's 10K, 1K, 100K. And they also need to know, what the dimensions of that resistor are, because the specific footprint is for a specific form factor. In this case, it's an 0402 form factor chip. But there's loads of different form factors of resistors. So you need to know exactly which one to go on the board, and they need to know then which part matches, so it'll be able to be soldered onto the pads that they've put onto the board. So in my case, I use JLCPCB as my manufacturer. So JLC PCB conveniently give you this thing you can search for, which is this whole parts library that they maintain. So if I search for, say, a 1K resistor, so I type in 1K, and I get a ton of different results here. So you can see these are all like 1K resistors. They all have different specs, which is partly, again, why you might need the part number, because they need to know which of these resistors there are. And you see there's 6,837 different 1K resistors that you could put in, or, well, parts that match the search term 1K. You also notice that the stock is 0 for most of these. So they have this on their record, but they don't necessarily have it in stock. So if I picked to add this resistor to my board, they might not even be able to do it because they don't have any of them. So you can filter this. So if I filter by the ones that are in stock, you'll see, okay, so here's a 1K resistor I can use. This is the manufacturer. We've got a ton of them in stock. So if I want to use this one, I click in here and see, oh, damn it, JLC. Why you got to do me like that? Yeah, there we go. So it's giving me, this is the resistor, and it'll give you all the electrical characteristics and stuff of it. So you can, I don't know, so you can look at the data sheets, you can see what it is. But then the other key point is that they have this part number here. So this part number is the unique identifier for that exact resistor that has that footprint and that value, and that's what JLC will put on my board. But I need to tell them that. So the way you do that, in our parts library here, you have to set up in the attributes this thing here. So you'll see it's got this LCSC part, and that matches that part number. You notice that LCSC isn't JLCPCB. The part numbers match because they use this LCSC. They're the supplier who supply all the parts to them, so they match. I think they might be the same company. I don't know why the initials are all different, but they're in some way related anyway, so that these part numbers are identical between, if you see an LCSC part number is the same as a JLCPCB part number. So all of these parts here, which are all of the parts that I'm using on this board, they all have that value assigned to them. And yeah, so they're set here as this special property. And where that really comes in is at some point you need to export what's called a BOM file, a bill of materials file. And when you do that, automatically there's a script you'll run that can export that. It will pull out that LCSC part number, stick it into the BOM, and then when you want to manufacture it, you upload that to JLCPCB's website, and it matches up all the things. And that's how it knows exactly which part it needs to put on the board. And if you don't supply that BOM, you can't have the boards assembled. So you can have it manufactured, but they won't assemble it then because they don't know the parts and stuff. So that's just a little bit about the setup and things like that. So this is like where it starts to get, there's a back and forth with this that can be quite arduous to set up, is that you have kind of a chicken and egg problem. I want to design my board, I want to start drawing my diagram, and I want to put my parts in, but I don't know what parts I want to use yet. And then I need to go off and do all the legwork to assemble this parts library with all these parts before I can do anything with drawing it. So there's this, it's a little bit convoluted. There are systems that make this a bit easier. So Easy EDA is a system that's supported by JLCPCB. You see this if I click this PCB footprint or symbol. So I have the symbol here and I have this footprint, and you can install this basically in Easy EDA, but it is a paid thing you have to pay for. So the thing, like there isn't free part libraries for everything. Ideally, you'd absolutely love if every part that was in JLCPCB had a library that was mapped perfectly into Eagle or Fusion in this case. But why would they if they're not getting anything from that? That's a lot of cost and expense and difficult stuff to manage for no return for them, really. There are like big companies that do this, and like there's a platform EDA software called Altium, which is, as far as I know it, it's basically about the gold standard. And there's people whose jobs it is in companies that do this stuff professionally, who their main job is creating and managing a parts library in Altium, which would have all this nice stuff in it and have all the part numbers in it, and everything would be perfect. And a lot of people will also like draw all of this stuff themselves. So I should say, like, I didn't, I didn't draw and assemble these myself. I was able to download these. So there's different places where you can find the packages and find the footprints, and you can kind of cobble them together yourself with like the importing tools up here. So that's mostly how I've done it, which is why some of these look different than others. Like, for example, why some of my resistors are these squiggly lines and some of them are these square lines. And that's just because I just found that package that matched and I imported it and it works. So it doesn't really matter. But if you wanted real consistency, you would draw these yourself. I don't necessarily have the patience for that, but some people do. And if it's your job, then it makes sense to do it, maybe. I know that's the advice that a good friend of mine who is a professional at this, he designs all of his himself, and that's what he does. He's gotten very quick at doing it. I still find these tools difficult to use, so for me it would take me so long to do it. I'd probably just tear what little hair I have out doing that. So anyway, let's have a little look then at the circuit. So if you've watched my other video, you'll know this circuit, maybe you might have seen it. But yeah, this is basically our switch here, which connects between the source voltage, which I've just written as 9 volts, and ground. You can see here it pipes through to the base of this transistor, and then the collector of that transistor goes to the source and gate of this MOSFET, and then the output of that is what will go to my regulator. So this is effectively the switched output. So if I was to do that 5th pin that I talked about, I'd take a tap from here, pull it out, and stick it over here onto the pin headers to get the switched pass-through voltage, basically. So at the moment, that just goes straight into this regulator, which is my 5-volt regulator, and this regulator, which is my 3-volt regulator, 3.3-volt regulator. And yeah, I don't want to go too much into this because it's a bit convoluted, but effectively you can think of it like this. When this is switched from ground to high, the base of this starts conducting. So this switch, effectively this transistor turns on, starts conducting, and then the difference in voltage here, because this allows current to flow here through this circuit, which is for the source and gate of the MOSFET, allows the MOSFET to start conducting. So the V-in voltage here, which goes to the source, is allowed to conduct through to the drain of the MOSFET, and then this goes to whatever the source voltage is. So V-in here appears here, and then if you turn the switch off, the transistor stops conducting, then the gate here basically won't be turned on, and then at that point the source to drain voltage or current will drop, and there'll be no voltage there. No voltage will appear here, which effectively turns off these two regulators, and if I had my other tap, it would turn off something that matches the supply voltage. Only other thing that's here is we have this capacitor that runs a 100 microfarad capacitor, which is fairly big, runs between the output voltage and ground, which is supposed to help with power supply ripple, basically. These are linear voltage regulators, so they're not the most efficient things in the world, especially if you were to say try and drop 12 volts down to 3.3 volts. These will heat up quite a bit, but because they are these linear voltage regulators, they don't have a lot of ripple on them. So by putting this capacitor here to help with the supply voltage ripple, should be pretty smooth what comes out of it. Another version of this, maybe V3 version, is to change these linear voltage regulators to switched regulators. If I did that, I'd probably have to put some smoothing caps on the outputs of these regulators, because the switching regulators will have more ripple in them. So that's something that will have to be done. But for now, I think this should work. So yeah, we'll see how much utility I get out of these. I have a feeling I really do want that 5th pin that goes on the output here. So yeah, I may have to address that. Okay, last bit then. Let's have a look at the layout for the circuit board. So this is the board layout. The way this works in general, what'll happen is at the very start of this process, you'll click to generate your board. It'll dump you onto this page. There'll be this yellow rectangle, which you can size to whatever size you want. It snaps to this grid. The grid is set up to be, the pitch basically is set up to be multiples of 2.54 millimeters, which is kind of standard electronics pitch. It's like the gap between pins on a breadboard. And yeah, you then start, all your components will be like off over here to the side, and they'll have these little like lines connected between them that show that they're connected, but that there's no traces run. So what your job then is to drag the components onto the board, start placing them, and then start routing the board. So routing the board means those little fine lines that are between them, you start drawing the actual copper traces, which are like all these guys here. And you'll see in this diagram, they all have names. So this is 5 volts. So I know everything here is going to have 5 volts on it, including the 5-volt pin here. And that matches, when you go back to here, everything here that I've labeled with 5 volts. So it's a little bit hard to see, but I can highlight it if I go to maybe this. Will this show me? Yeah, so you can see here, it lights up in blue, everything that's connected there. And same here, I can see that that's V in, everything that's connected to V in gets lit up there. And then those labels are all the exact same as the labels that appear on these. So it makes it very easy to route the board if you've labeled everything sensibly and can kind of map it out. Yeah, I don't know, there's not a huge amount to say about this. I've been told that routing boards is kind of a bit of an art form. I wouldn't say I'm terribly good at it. I've managed to get this one done. I've done 2 now, and I guess I'm kind of picking up learning bits and pieces. But yeah, I wouldn't say this is, I'm not saying this is a masterclass of any sort. This is just something I've cobbled together and, sort of looks like it's working. Some cool things you can do. You can like toggle between different views of this board. So you can turn off the bottom or turn off the top view. So now this is effectively what would be on the underside of the board. So boards can have multiple layers. JLCPCB, the most basic version they have, is a 2-layer board, so it has a top and a bottom, and that's all I've designed here. It's just a 2-layer board that has a top and a bottom. So I have the top, I can have the bottom, I can toggle them on and off. And having the 2 layers is just useful because it allows you to route things around each other without them running into each other, because obviously all of these lines, they can't intersect with each other because they're physical, pieces of copper that are carrying the signals, so they can't cross over each other, they can't intersect, so they have to move around each other, which is why you'll see, so if I hide this, you notice this little path here has to go from here and go whoop, 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 all the way around to get to here, because it can't just jump over anything else. So by having a bottom layer that you can throw a bunch of traces into, you can have things that effectively cross each other because they're physically separated on opposite sides of the board. Yeah, I don't want to talk too much about this because I'm no expert. I've just basically cobbled this together for something that works. But if I've managed to do it, I think most people can probably figure it out. It's not the most complicated thing in the world, but it does take a little bit of patience and skill to work on it. One thing that I did discover, and I learned this the hard way, there's this wonderful thing up here called the DRC, which is the design rule check. And if you click this, it will automatically use its smart software brain and check the circuit to see if it has any obvious errors. In this case, it has no errors, which is really great. So, because it gives you enough freedom to completely screw this up and miss things and like cross things and attach things. If you run the design rule checker, it'll check everywhere where there's copper, and it'll make sure that all the connections are actually connected and make sure that everything works the way you think it does. It can't correct for a design that won't work, but it can correct for mechanically have you connected everything properly, which is really, really good. So yeah, I think I'm going to leave this here. This is kind of a little bit of detail that I've gone into here. It's kind of abstract. I hope this helps someone. I don't really know. I feel like I've just been talking through some of my thought process on how this works. I haven't gone into huge detail on anything. Maybe there's some nuggets in here you might find useful. If you have any questions about this, please leave them in the comments. I'd love to hear people's thoughts on this, because, when I was first starting this, I had to ask loads of questions. I had to really bother my good friend who is a professional at this and ask him all these dumb questions, what I thought were dumb questions anyway. Um, but yeah, there's a lot in it. It's very detailed. I've managed to scratch the surface a little bit, and I'm having kind of some fun doing it. Um, so yeah, that's about it for this one. I do plan to do more electronics design in the future. I really want to get into doing some more complicated PCBs and make my own custom boards for things. I have a plan to build my own little like STM32 dev board this year. This will hopefully be part of that, like a modular, daughter board system that I can use. But yeah, that's all to come. Want to see if this one works first. So yeah, I will grade another video in like 2 weeks time or so. Whenever that board comes, I'll let you guys know if it worked or not, and you can see it. So anyway, if you've made it this far, thank you very much for watching. It means the world to me. And yeah, I will see you guys in the next one. Bye bye.